So, good morning, everyone. Good evening. I would like to welcome you to our third session on data analysis, or that is qualitative and quantitative methods. Yesterday we did have a session, and I think it was okay because I have not received any comments or questions from the students or any scholars. So I would like us today to proceed with correlation and regression analysis. So having mentioned about qualitative and quantitative, so we move on to quantitative, and if we can remember very well, we said that in quantitative we have descriptive statistics and inferential statistics. We did mention about the descriptive statistics. So we are looking at inferential statistics, and on inferential statistics we start with the basic correlation. Then we will move on to regression. I think for today we are going to just cover the two areas about our quantitative analysis or quantitative methodology. So what comes into your mind when you talk about correlation? So when we talk about correlation, we are testing linear association between continuous variables. So we have continuous variables and we want to establish if there is a linear association between them. As well, interpret the result of the correlation coefficient. So when we run the correlation, we have the correlation coefficient, which we are going to see how to use in terms of making inference or when commenting on your data. So the purpose is actually to measure the direction and the strength of the linear relationship between two quantitative variables. So when we have two variables, quantitative variables, then we want to establish the direction. And when we talk about the direction, we are just talking about it can be a positive direction or negative direction. So we would like to establish the relationship or the association between two variables and the movement. So if presented in a graph, it could be, for instance, an increase in, which means an increase in x leads to a similar change or increase in y, or the reverse, which means when one variable is increasing, then the other one is decreasing. So there are some assumptions that underlie the correlation analysis, and one of the assumptions is that we use scale measurement level, which means we only use variables that can be able to be measured in terms of we are comparing two variables which have a scale measurement. From our first class, we talked about the ordinal, the scale, and all that. So very, very important. And another one is that your data must be normally distributed. So if you have data that is skewed, which means it is affected by outliers, then it may not be it may not be the best type of data that will help you in conducting a correlation analysis. So you must have data that is normally distributed. For instance, data that if you represent in a normal distribution graph, then you can see that the data is not affected by extreme values. So that is it. So one of the main things that you need to understand in a correlation analysis is that the values of a correlation must run between -1 to +1. So if you conduct a correlation analysis and you establish figures outside this, then you know that your correlation analysis is not okay, because the values or the figures, they must be between -1 to +1, whereby if we have -1, then it means there is a negative correlation. If you have a value of 0, then it means there is no correlation. If you get a value of 1, +1, it is perfect positive correlation. Perfect positive correlation. -1 is perfect negative correlation, and +1 is perfect positive correlation, which means that if you represent in a graph and you get perfect positive correlation of 1, it means a change in y leads to an exact change in x. So that is, it means the gradient is equivalent to 1. A change in y is equal to a change in x. So that is perfect positive correlation. Negative correlation means that one variable is increasing, the other one is decreasing. So for instance, if you get now, of course, your result, they don't have to be 1, 0 or 1, but they can be in between. So if you get a value of say above 0.6, we say it is a strong positive correlation. Some scholars say from 0.7, 0.8, it depends, but from 0.6 onwards, your correlation is strong, positive. If you get between 0 and 0.5, that is a weak positive correlation. Weak positive correlation. If you get negative, that is between 0 and 0.5, negative, that is a weak negative correlation. Weak negative correlation. And if you get above -0.6, you say that is a strong negative correlation. So basically, I hope you not be confused. The direction, the negative sign or the positive sign just shows the direction or the movement of your graph. So if you represent that data on a graph, it means you are going to see the direction, whether it is negative or positive. Okay, so maybe I will share some examples later on how it should be done in SPSS, but basically that is what you need to understand. Because the moment you understand the values and how to interpret, then in SPSS it will not be very difficult for you. So sometimes we also have what we call a partial correlation. So when we talk about a partial correlation, it's actually testing a linear relationship, but you have a third variable, which we call a controlling variable, which can be continuous a variable. So you need to understand that you can conduct a partial correlation when you have a third variable, which is a control variable, because in some instances, when you are testing a relationship between two variables, there can be a third one that affects the two variables indirectly. So that is why we conduct a partial correlation. The output is interpreted the same based on the values that we are talking about. That is between -1 to +1. So you expect, whether you are doing a normal correlation or partial correlation, then the values must be between those variables. So that is basically about correlation. I think today our class is not going to be too long because we are just covering two aspects. The next one is multiple regression or just regression. Before we go to the multiple regression, it is important to understand regression in general and know why we conduct a regression analysis. So basically, we are going to look at how we are going to calculate and interpret a simple linear regression equation. Then the assumptions behind a regression analysis. Because when we conduct a regression analysis, there are some assumptions that must underlie. There are minimums that must be met before you conduct a regression analysis. Then we are going to look at the application in terms of prediction, because regression analysis helps us to make predictions by use of a mathematical model. Then later we will look at on how to recognize nonlinear relationships between two variables. Because basically when we talk about a regression model, we are trying to establish the cause and effect, or the relationship between variables, that is more than two variables, which affect a dependent variable. Of course, there are some fixed elements that we are going to look at when we construct the regression model. So a simple regression model is represented or presented by y is equal to b plus b1x. You can say a plus bx, any form. That what you need to understand is that we have the predicted or the dependent variable, which is y. Then we have the b naught, which is the y-intercept. Sorry, the regression intercept. That means when x is equals to 0, then y. That is actually the y-intercept, yes. Then b1x, the b1 is the regression slope, that is the gradient, and then we have the independent variable. So when we talk about the regression, it must have a dependent variable, independent variable, we have the y-intercept, and then we have the slope of the line. The slope is the change in y over change in x. I don't want to go into mathematics, but just the basics on what you need to understand. So before we proceed, I would like us to look at the assumptions that must be met for us to conduct a regression analysis. The underlying conditions that must be met for us to conduct a regression analysis. Number one is the normality. You have to ensure that your data is normally distributed. So we mentioned this in correlation analysis as well as now in the regression analysis. And it is very important for us when we talk about normal distribution of data, because if you have data that is affected by figures or values that are too high, say for instance you are talking about the salary, you have most of the employees getting between 20,000 or 2,000 euros to 5,000. Then you get this one person who's getting 10,000. So if you can get the average salary of these employees, the figure you are going to get is not going to portray the real situation or scenario in the market. This is simply because one of the employees is getting a higher salary as compared to the others. And this is one of the main things that we have to consider when we are constructing our regression analysis. We have to ensure that our data is normally distributed. And how do we do that? We have different ways of testing for normality, which maybe we can use later. We can use a histogram. You can draw a histogram and see how your graph behaves. If it has extreme values, then if your data is not normally distributed, then it means you are not going to use a correlation analysis, a regression analysis for your data. Next is linearity. Linearity is a very, very important aspect in testing for a regression analysis, because we assume that your variables are linearly related. That means there is a linear relationship between those variables. So if you cannot be able to establish a linear relationship among your variables, then regression analysis. I don't know why I'm talking about correlation, but it's just because there is a, when we talk about linear, actually we are talking about correlation. That's maybe why I keep on repeating about correlation. Sorry for that. We are talking about regression analysis and the assumptions. And the second assumption we have talked about is linearity, where we are saying that your variables must be linearly related. Okay. The other assumption is homoscedasticity. Homoscedasticity. I know it is like a tongue twister, but it is called homoscedasticity. So when we talk about that as one of the assumptions of regression analysis, it refers actually to equal variances of errors across all levels of the independent variables, which means that researchers assume that errors are spread out consistently between the variables. So when we are talking about this, we are saying that the variables, the errors are spread out consistently. We don't expect to have some variables being affected highly by some errors as compared to others. So if that condition is not met, then regression analysis cannot be one of the best measure of our relationship. The other one is multicollinearity. Multicollinearity. So when we talk about multicollinearity, we are looking at whether our variables are affected by, they are highly correlated. We look at correlation among the variables and check first before we conduct a regression analysis. We look at how the individual variables are correlated. So if these variables are highly correlated, then that means it is going to affect our regression model. And how do we conduct multicollinearity? We have the variance inflation factor, which we use as one of the measures of multicollinearity, or the tolerance variable. So we are going to see on the decision rule, at what point do we say that our data is affected by multicollinearity. So we are going to give an interpretation to the values that we get. Basically, when we talk about tolerance variable and the variance inflation factor, they are related. I think I'm going to mention that when I start talking about the real regression model. So for now, you have to understand that that is also one of the conditions that must be met in conducting a regression analysis. Another assumption is the independence of error terms, which refers to the assumptions that errors are independent of one another. So the errors that affect our variables are not dependent on one another. So that is the last assumption that must be met in order for us to consider a regression model or a regression analysis for our data. Now, when we conduct a regression analysis, what are we expecting to get from the output? Of course, we are going to see this when we are going to use the SPSS and see how to run a regression analysis and the output that we expect to get. So in a nutshell, a regression analysis actually is like we draw a scatter diagram. A scatter diagram shows different distribution of data in a graph. So we are trying to establish the line of best fit. So the line of best fit, it means it's like an estimation line that we can be able to establish a relationship between the dependent and independent variables. Of course, we have fixed terms. So one of the main thing to look at when you have your the output from your regression analysis is the coefficient of determination. So the coefficient of determination is shown as R squared. So when you conduct your regression analysis and you get your result, which we are going to look at when we will be dealing with a practical example using employee data. Actually, I will request that each one of my audience to install SPSS of any version and then try to search for employee data. Employee data is just a customized data that comes with SPSS. That is what we are going to use when we will be doing illustrations. It's now to understand the basic and know what we expect. So when we will be doing the practical part, we will be knowing which kind of values to look at and how to interpret them. So the coefficient of determination as an output of the model summary indicates how well or how good the regression equation fits your data. We said we develop a regression model based on line of best fit from a scatter diagram. So the R will show you if the regression, your data is good for the regression model. Of course, the R that we get from the regression model will be interpreted the same as we talked about the R in correlation analysis, whereby if you have, for instance, 0.6, you can multiply that by 10 and say 60%, which means the R, for instance, if it is 0.67, then you multiply by 10, you can say is that your model summary, it's 6, okay, the model summary explains like 67%, or let me see how to put it in this context, because we are talking about how good the regression model fits your data. It's actually 67% based on the output. That is if you are given 0.67. Then we have the standard error of estimate as another output. Actually, before we go to the standard error, we talked about the R, then we have the adjusted R and the R. Actually, when you conduct a regression model and you get R square and adjusted R, if they are closely related, then it means your data is also fit for the regression model. Very, very important. The other one is the standard error of the estimate, which is the measure of accuracy of prediction. Because we said the regression model has quite, for instance, if we talk about multiple regression has a number of independent variables that affect the dependent. So when we talk about the standard error, we are looking at the accuracy of the predictions of each variable that affects the dependent variable. Very, very important. Actually, sometimes the standard error of the estimate is also called the sum of squares error. The sum of squares error. Very, very important. Of course, we cannot forget about the p-value, the sig value, and this most of the students get confused. Actually, I was also sometimes being confused because I didn't understand, like, how do we interpret the p-value. That is now, when we talk about the output, actually, the first one was the model summary, which has the R square, adjusted R, and the standard error of estimate. Then, the next table we expect to get from the output is the ANOVA. And in the ANOVA table, we use the p-value or the sig value. Sometimes we call it the p-value or the sig value, which we use to establish the level of significance, or to check the statistical significance among the variables. So we have the decision rule. For instance, if the p-value, actually the decision rule is that we check the value, or the p-value, or the sig value that we get from the ANOVA table, and compare it with 0.05. So if it is below 0.05, then we say the model is significant. And if we get the p-value or the sig value is above 0.05, then it means that the model is not significant. Very, very important, the p-value. In most, actually, when you get the output from SPSS or any software, the p-value or the sig value is one of the most important, variable, or is one of the, it's actually one of the most important figure to use in making an inference. Very, very important. If you conduct a correlation analysis, you will see the p-value or the sig value. If you do a regression analysis, you will see the sig value. If you conduct, for instance, analysis of variance, or you are testing a hypothesis using like, for example, independent t-test, or any type of analysis that you are doing, mostly you will get the p-value, which will guide you to establish the level of significance in the model that you are establishing, or in the relationship. Because for instance, you are trying to check if the output is as a result of chance, because sometimes we can say there's some things that happen due to chance, but not due to, it cannot be proven statistically, but it happens due to chance. So that is why we use the p-value to establish whether the relationship that occurs between the variables is due to chance, or has a statistical significance based on the value of the p, as we have looked at. So let us talk about the multiple regression. So that was basically simple regression. So when we talk about simple regression, it's actually we are looking at one independent variable affecting the dependent variable. Then, of course, with our y-intercept, that is if x is equals to 0, what happens? For example, in a business, we know that profitability of a business is affected, or there are different factors that contribute to the profitability of a business, or the cost, the total cost of a particular business. We have fixed cost and we have variable cost. So which means before you variable cost, actually they change with production. Variable cost change with the level of production. So what we mean is that, for instance, in a business, before you start producing, you have fixed cost. We have, for example, rent. That is a fixed cost. We have electricity. To some extent, we have a fixed cost, and a variable cost depending on the amount of units that you produce. So very, very important. That is a simple regression. But when we talk about the multiple regression, we are now bringing in more variables that affect the dependent variable, and that is a multiple regression. So when you talk about a multiple regression, we are actually using two or more independent variables to test the relationship. So, and we are trying to explain the variation in those continuous or the dependent variable. So we have a number of variables that we are trying to establish the relationship they have with the dependent variables based, and then of course these particular variables also they have some elements that affect them. So for instance, from our simple regression model, simple regression, which is y is equals to b naught plus b1 x1, then we can develop a multiple regression where we can have now y b naught b1 x1 then plus b2 x2 plus b3 x3 all to bn xn, which means a multiple regression analysis can be affected by many variables of concern to a particular researcher. So basically, we must have a dependent variable or a dependent scale, which we call y, and we must have two or more independent variables, which we call x. The assumptions we talked about, and the model actually we have talked about. Y is equals to a plus b1 x1, b2 x2, b3 x3 all to bn xn. So a is actually the intercept, the constant when x is 0. That is the y-intercept. Then b is the coefficient or slope of each variable. So each variable has a coefficient that affects that particular coefficient, that affects that particular variable. So each variable is attached with a coefficient. For example, in x1 we have b1, which is the coefficient or the slope. Then we go to x2, b2. I think it would have been very important if I would project the regression model, but I think we can do this later. So I just want to give an example. For instance, if we want to look at the total disposable household income, so we want to look at the fact that the dependent variable being total disposable household income. So what is it that affects that? That is what we call the independent variables, which are x. So total disposable income or household as our dependent variable is affected by value of goods produced for own consumption. So the value of goods produced for consumption can be one of the contribution to total disposable income. Then we can look at the family, all children related allowance. So the summation of the allowances of all children can also add to the total disposable income. Then the other one is the interest, the dividends or profits from capital investments from businesses. So if they are in a family, if you have some businesses, you get interest from investments, dividends from investments or other capital investments, then that contributes to the total disposable income. We also have income from rent of a property or land. So if you have land or you have property that you are renting, then you get some income. Then we have interest repayment on mortgage. That is also one of the factors that affect the disposable income or contribution. Then we have household allowances, regular taxes on Commonwealth, or tax on income and social contribution. So all these have a different impact on the disposable income. We have those ones that are adding to the disposable income, and we have those ones that are reducing the amount of disposable income. So for instance, the net total disposable income per household, if we talk about the value of goods for own consumption, that would decrease the dependent variable. When we talk about family and children related allowance, that increases the disposable income. Interest, dividends, that increases. Income from rental, it increases. Interest repayment on mortgage, if they took a mortgage, that reduces the total disposable income. House allowances, if you get allowances from your employer, it is increasing the dependent variable, which is disposable income. Regular taxes on wealth, they reduce the disposable income. Tax on income and social contribution, they reduce on the total disposable income. So it is very, very important to establish the kind of relationship that exists between variables, the independent variables and the dependent variable. Very, very important. And that is why we get now from the output or the model summary that we get, we are going to get negative and positive values or values, which means that from the values we are able to establish inverse relationship, which means if total disposable income increases, then we have those variables that decreases, and if it is decreasing, we have those variables that are increasing. So very, very key to understand the type of relationship or the direction with which the variables move. So what is the purpose of this regression analysis? We just mentioned that we use this multiple regression in predicting a dependent variable from two or more independent variables. So that is why we are saying that from the output we will be able to see the type of influence that one variable has to the dependent variable. So the interpretation of our model summary is just the same as when we talk about the simple regression. So one of the things we get is the model summary. Model summary also with the R square, adjusted R, and the standard error of the estimate. So when we talk about R, we are talking about the degree to which two or more predictors, that is independent or X variables, are related to the dependent variable. So actually the R in the model summary shows the correlation coefficient among these variables, or between the dependent variables, the dependent variable and the independent variables. So we are looking at the linear relationship between the independent and dependent, denoted by R. Actually, R, mostly we use the Pearson correlation coefficient or the Spearman's rank coefficient. So it depends with which one. The interpretation is the same, but mostly we use the Pearson correlation coefficient, denoted as R, and from our model summary it shows the degree to which two predictors, that is the independent variables, are related with the dependent variable. Then R square tells us what proportion of the variation in the dependent variable is explained by the predictors. Of course, from the output we get, it doesn't mean that all the variables, the independent variables, affect the dependent variable, but there is a percentage of effect that they have. There are other factors that affect our dependent variable which are not explained in our regression model, and that is why we talk about the R square. It shows the contribution of these variables or the predictors to our regression, to our dependent variable. For instance, if you get 50%, you can say 50% of the variance that is brought about on the dependent variable is explained by the predictors. So those particular predictors of concern that you are studying, the contribution they have on the dependent variable is what is explained by the R square. And then we have the adjusted R. So when variables are added to the R to the model, R square will increase or stay the same. It will not decrease. So which means that if you add two variables and then you increase more factors, the R square will keep on increasing, because we are looking at the contribution of each variable to the dependent variable. That's why we are saying if we include or we add more variables or factors into our regression model, then the R square will increase, but there is no point, at no point will the R square decrease. We have the standard average, the standard error, which shows the average deviation from the regression shape. And of course, the next table is the ANOVA table, which shows the p-value. And we talked about the p-value or the sig value, and we said if it is below 0.05 as our decision rule, then we say our model is significant. If it is not, or if it is above 0.05, then we say the model is not significant. The variance that is seen or established may have occurred due to chance. You cannot support that statistically because the p-value is above 0.05. So also we have the coefficients. Now the coefficient is our last table in the regression model, which helps us now to deduce the exact model, the exact correlation, regression model. Now we have unstandardized coefficients, we have standardized coefficients, and we have collinearity statistics. Actually, before I forget, let me mention that when we are checking for the assumptions of a regression model, we did mention that we can use tolerance or variance inflation factor to measure multicollinearity of the variables. And if we are using the tolerance, we are saying that the variance inflation factor, actually the variance inflation factor and the tolerance are just reciprocals, which means if for example the one is 0.2, then the other one is 1 divided by 0. It's just the reciprocal of the other. So the tolerance value or the tolerance variable is the reciprocal of the variance inflation factor. And if we get a variance inflation factor of less than 10, or if we get a variance inflation factor of less than 5 or 10, sometimes actually yes, some scholars say below 5, others say 10. So then it means multicollinearity is not affecting our model. So we use the 10 or 5 depending on which scholar or authority, but mostly we use 10. So if you get the variance inflation factor to be below 10, then it means multicollinearity is not affecting our regression model. So we use the unstandardized coefficients, and we use the unstandardized coefficients to denote our regression model. So because I think I have not projected the regression model, I cannot be able to comment on these the constant and all these variables. But one thing you need to understand is that from your regression coefficients, you have the constant, and then we have the different components and how they affect our dependent variable. And remember, if you get a negative value, then it means there is an inverse or negative relationship. And if it is a positive, it means the variable has a positive contribution towards your dependent variable. So basically, actually, if the tolerance has to be, I just want to clarify that the tolerance has to be greater than 0.2, or variance inflation factor must be less than 5. That is, if we need to say that our model is not affected by multicollinearity. Sorry for that mix-up, that I have clarified that although there are some scholars who say 10, but in this scenario, if the tolerance is greater than 0.2, or variance inflation factor is less than 0.5, less than 5, then we say that multicollinearity is not affecting our regression model. So I think that is what we wanted to cover today. Maybe to remind ourselves, we talked about the correlation, and when we mentioned about correlation, we said that it is used to measure linear relationship between variables, and the values range between -1 to +1, where if it is -1, it is negative correlation. If it is 0, no correlation. If it is +1, is a perfect positive correlation. Remember, a value of above 0.6 is a strong positive correlation. A value of above -0.6 is a strong negative correlation. Between 0 to 0.5, positive or negative, it means we have a weak correlation. Then we talked about the regression model, from simple to the multiple regression, where we talked about the simple as using one variable one predictor variable to check its influence on the dependent variable. And then we talked about multiple regression analysis. As the word connotes, it means we have multiple variables that affect our regression model. Remember the assumptions of normality, linearity, and multicollinearity, among others, and how to interpret. Remember also about the R, which is the output that we use to derive meaning out of our regression model, where we talked about R as the correlation coefficient, and then adjusted R, which shows the contribution, the R square, which shows the contribution the predictors can be able to explain to the regression model, to the dependent variable, and then adjusted R. Remember also the p-value that we talked about. If it is above 0.05, then it means the model is not significant. If it is below 0.05, then it means your model is significant. Yesterday I did mention that I will be sharing my email, but I forgot. I will post, and actually I have downloaded or uploaded these videos onto my YouTube channel. I'm requesting you to subscribe. They are not maybe it's just as for the beginning. The videos may be they are not very quality videos, because I just upload them the same way from the phone. So maybe in future I will try to see how to make the videos very interactive. But for now, you can subscribe to the YouTube channel and follow if there is anything that you would like to be clarified. Feel free to correct me if there is something which, because I don't have monopoly of knowledge. If there is anything that did not come out clearly, you just share with me. Learning is a continuous process, and if there is anything that you need to be clarified, you can also write directly to me. Then we can be able to see on how to improve ourselves. Until we meet again, I'm not sure whether we have another class tomorrow. But before the end of the day, I will post if we have a class tomorrow to proceed with the remaining parts. I really wish to appreciate you for your time. Thank you very much, and have a great morning, a great afternoon, a great evening. Thank you very much. Bye.